Hi, good afternoon, everybody. So what am I going to do here? I'm going to use, so many of the presentations we've seen at this conference apply computational analytic methods to data that itself was collected on a computer. In contrast, in the work I'm going to describe here, I apply computational analytic methods to a very traditional kind of data. I mean, it's a type of data that's had a long history in the learning sciences, and that's videos of interviews that are intended to study kids' prior conceptions in science. And I think that's a sensible thing to do for a few reasons. But most importantly, it's because this is well-traveled territory, I know a lot about what constitutes a deep analysis of the thinking and learning. And that puts us in a position to see what computational techniques can really do to capture deep features of learning. So that's what I'm going to do. I'm going to try to automate the kind of analysis, traditional analysis, that I usually do by hand. And crudely, you can think of that analysis as having two pieces. The first piece is to identify a set of conceptions, and then the second step is to code the data in terms of these conceptions. And I want to automate both of those steps. Finally, given that this is my objective, I think it makes sense to start with simple methods and ride them as far as possible, so you can really get a sense of what each kind of analysis does for you. Okay. Before diving in, I want to do just a little bit more to set the stage. So the data I'm working with will be 54 interviews with middle school students, and I'm going to look at a portion of those interviews where students are asked to explain the Earth's seasons. That makes sense because it's a very highly studied piece of subject matter. And the analysis approach I'm going to use combines simple vector space models with clustering. And finally, before starting, I wanted to point out that the reason to think automating the analysis of this kind of data should be really difficult. The amount of data is very small compared to what we usually have to work with in learning analytics. The student's speech is halting and ambiguous. It's difficult even for human analysts to understand most of the time. And gestures and diagrams are also an important part of the communication, and the automated analyses aren't going to have access to any of that. Okay. Now I want to tell you just a bit about prior conceptions research in science, prior conceptions in science. When I talk about prior conceptions, I'm talking about the prior understandings that students bring to science learning. So it's pretty widely accepted in the science ed literature that many of the key problems in science instruction revolve around issues relating to student conceptions. And there's just been a huge range of research on prior conceptions for that reason. In fact, there's a prominent bibliography that was compiled in 2009 by Dewitt and colleagues, and that lists over 8,000 papers across a huge range of domains. Okay. So it's common on research on prior conceptions to contrast two theoretical poles. So one pole I'll call the theory pole, and according to that tradition, prior science knowledge consists of relatively well-elaborated theories. And the other extreme is the knowledge in pieces pole, and according to that perspective, prior science knowledge consists of a moderately large number of not well-organized conceptions. So my own point of view lies closer to the knowledge in pieces perspective, and that has important implications for the type of analysis that I do. So the way I understand it, when you ask a student a science question, what they do is they construct explanations in the moment, drawing on sort of a large set of conceptions that they have available. So for my analysis then, I'm looking to identify those conceptions and to understand how a student draws on them to construct their explanation in the moment. So as far as I'm concerned, for a computational analysis to be worth its salt, it needs to be able to produce that kind of analysis. Okay, so now I'm going to give you more of a sense for what the corpus looks like. As I said, I have 54 interviews with middle school students, and the interview protocol went roughly like this. First, our interviewer would ask, why is it warmer in the summer and colder in the winter? Then they'd have time to ask follow-up questions for clarification. Then they asked the student to make a drawing, and then they could ask for more clarification. And then the interviewer was also prepared with challenges for certain answers that a student might give. And we really see quite a diversity of explanations in these interviews. They're kind of all over the place. It really feels like kids are putting together pieces as they answer. But I can still give you a sense for kind of the range of explanations that you see. So one family of explanations we call closer-farther explanations. So in those explanations, the whole Earth orbits so that it's sometimes closer and sometimes farther from the sun. And when it's closer, it's warmer. There's a family of explanations that focus on the side of the Earth facing the sun, side-based explanations, and the side facing the sun is warmer. And then there's a variety of explanations we call tilt-based explanations, and those include but aren't limited to the correct explanation. In those explanations, the hemisphere tilted toward the sun has summer, and the one tilted away has winter. Okay, and now I want to just talk you through 3 specific interviews that I'll kind of use for reference here. And the first interview is with a student named Edgar. And Edgar started off by giving a version of a side-based explanation in which he emphasized the role of the sun's rays. And I'm just going to read the underlined parts here. So he says, and the rays hitting like directly right here, and he's pointing to the side of the Earth facing the sun. Once this thing turns, the country will be here, and the sun can't reach as much. But then, after just prompted by the interviewer to elaborate a little bit, Edgar shifted spontaneously to give a pretty typical closer-farther explanation. And he said, that thing is like I'm further away once it orbits around the sun. Earth, I mean the sun. Okay, so hopefully it's clear from this the speech isn't that easy to understand and that a pure text transcript loses a lot of important information. Okay, so that was an example in which a student shifted from one explanation to another. And now I want to quickly give you 2 additional examples in which students gave a single explanation, and they're both varieties of tilt-based explanations. So Zelda gave an explanation that's very close to the correct explanation. She said that the side of the Earth is tilting toward the sun, or it's facing the sun, so the sun shines more directly on that area, so it's warmer. So the side of the Earth, the hemisphere tilted toward the sun, feels more direct sunlight. And that's pretty much the right explanation. There's a little hint of side-based talk here that we might want to worry about, but what she's got is pretty close. And finally, Caden also gave a tilt-based explanation. But in his explanation, the hemisphere tilted toward the sun is warmer because it's closer to the sun, which isn't correct. He says the axis is pointing at an angle so that sometimes on the northern half of the hemisphere is closer to the sun than the southern hemisphere. Okay, so that's the data. So now I'll tell you about the automated analysis. And first I'm going to give you how it works in overview, and then I'll dive down in a few places. Okay, so first we clean the transcripts, removing everything except words spoken by the student. And then I break each transcript into 100-word segments with a moving window that steps forward 25 words. Those numbers were chosen heuristically, and there's more about that in the paper. So that results in 794 little segments of interviews. Then we map each segment to a high-dimensional vector. And then we deviationalize the vectors. I'm going to have to tell you what that means. Then we cluster those vectors, and we interpret the clusters, and then we apply the clusters to analyze transcripts. Okay, so now let me dive in detail in some places. So first, how do we map those 100-word segments to vectors? Well, there's many elaborate vector space models. What I've tried to do here is use the most vanilla method possible. So the first thing I do is compile a vocabulary of all the words that appear somewhere in the corpus. And then I remove from that vocabulary words that appear on a stop list of words. And the particular stop list used here is a standard one I've used for a while that has 782 words on it. And so that results in a vocabulary of 647 words. So it's a list that has words like this on it, plus a lot of others. Then for each of my segments, I count how many times each of the words in the vocabulary appears in the segment. That's that step. And I get a long list like this, but of 647 numbers. Then I reweight those numbers with a standard weight function of 1 plus the log of the count. So now the list looks like that. And that's nice because it has the effect of limiting the impact of very high frequency words. And then I normalize that vector that results. And then so what this produces now is instead of 794 segments, we have 794 of these vectors, each of which is a list of 647 numbers. Okay, so now what we'd like to do is cluster those vectors. So this is the one place where things get a little funky. It turns out that if you just try to go ahead and cluster the vectors, the 647-dimensional vectors, it's very hard to get anything sensible. I think the problem is that all of these vectors are about, all these little snippets are very, very much about the same thing. They're all about explaining the season. They all talk about the Earth and the Sun and how close the Earth is to the Sun. So what you need is a method to kind of split them apart, to kind of highlight the differences among them. And I tried a lot of standard approaches for doing that. In the end, I just found this one way of doing it that works. And it's this process I call deviationalizing, for want of a better word. If you think of a better one, you can let me know. So what I do is I average all the vectors and then replace each vector by its difference from the average. So what that would look like if you just had two vectors, then you'd find their average. So this is the average of V1 and V2 prime, and of V1 and V2, and then we replace them with V1 prime and V2 prime. So that's deviationalizing. And now we're in a position to cluster. And to cluster them, I used hierarchical agglomerative clustering. So probably most of you in this audience knows what that means, but I like to explain it anyway. So I start with each of the segments in its own cluster, and then I iterate. And at each iteration, I combine the two clusters that are most similar, and that reduces the number of clusters by one. So the result is that I start with 794 clusters, and I end with each segment in its own cluster. Then I end with one big cluster with all the segments in it. And to decide which clusters to merge at each step, I compute the centroid vector for the cluster. That's the average for that cluster. And I merge the two clusters that have the most similar centroids. So that process essentially generates a list of candidate clusterings of the data. So what I have here is a portion of a table are the sizes of clusters that are formed at various stages in the analysis process. So the bottom row, for example, says that when they're grouped into three clusters, I get a cluster that has 271 segments in it, one that has 279 segments, and another that has 244. And as you move up the analysis, up this table, the number of clusters grows and the sizes of the clusters shrink. And across a number of analyses, I found that working with about 7 clusters works pretty well. It allows you to sort of resolve interesting features of the data while also producing something that's not too terrible to interpret. So we're going to work with this row here that has 7 clusters in it. The next step is, what do these clusters mean? Okay, because these clusters are supposed to in some way represent the conceptions that we're trying to identify. Okay, so each of the 7 clusters can be thought of as identified by its centroid vector, the average of all the vectors that comprise it. Okay, and these vectors are in turn each described by a list of 647 numbers, and each of those numbers corresponds to a word in the vocabulary. So one way to understand the meaning of the clusters is to look at the words that have the largest value in each centroid vector. So that's what I've done here. So for each of the 7 clusters, I've listed the 10 words that are most characteristic of that cluster, ignoring some of the rarer words. So these tables have those words together with their value in the centroid vector of that cluster. Okay, and remember these are in some ways supposed to be our conceptions. So some of these lists are indeed very suggestive. So here's cluster 1, starts with the words tilted and towards. So that seems like a conception that should be an important piece of a tilt-based explanation. And then cluster 4 starts with side and facing, so that seems like it should play an important role in side-based explanations. And cluster 7 talks about farther and closer, so that seems like it should be a bit of a closer farther explanations. But these clusters, they're not supposed to necessarily align with full-fledged explanations of the seasons. They're just little bits of ideas you can build them out of. So some of the other clusters that are here, I think it's easier to see how they might align with smaller conceptual units. So for example, let's see, cluster 3 is about the hemispheres of the Earth. You often talk about the hemispheres in tilt-based explanations. Clusters 2 and 6 both are in different ways about the spinning of the Earth, rotation of the Earth. Cluster 2 seems to be more purely about the spinning of the Earth. Cluster 6 is about the rotation and the day-night cycle, which you do see in the data. And finally, cluster 5 is something about the rays hitting the Earth and especially hitting the Earth at an angle. Okay, so now we've identified a set of conceptions, and now we want to apply those conceptions to code the original data, to try to understand the original data. Okay, so here's what we do to do that. For each transcript, we again segment it into 100-word chunks in exactly the same way as before with the moving window. Then find the vector for each segment. And then for each segment, find the dot product between the segment vector and each of the cluster centroids. I want to find how close the vector for that little segment is to each of the vectors for the clusters I've found out, which correspond to my conceptions. And then I plot the result in a hopefully easy-to-interpret form. So now let's see what that looks like. Okay, so this is what we get for Edgar. So remember, Edgar started with a psi-based explanation in which he talked a lot about the sun's rays, and then he shifted to a tilt-based, a closer farther explanation. And this is what the analysis in terms of conception spits out. So in the first four, so we split into 10 segments. In the first 4 of those 10 segments, the blue bar dominates, and the second 6, the black bar dominates. And right around here, it turns out, is where he shifts between his 2 explanations. Cluster 5 was the cluster that has to do with the rays hitting the Earth. And remember, he did talk a lot about the rays. And then cluster 7 is the one about being closer or farther, which makes sense since he shifted to a closer farther explanation. So this seems to be capturing at least a lot of the flavor of the analysis that a human analyst gives of Edgar's transcript. Okay, so now let's look at Zelda. Remember, Zelda gave a consistent tilt-based explanation that was pretty much on target, or close to on target, where the tilting of the Earth caused light to be hit less directly on the Earth. And here's what we get for her. So she's only got 5 segments, and her analysis is dominated by this first red bar. And that red bar corresponds nicely to cluster 1, the tilted towards cluster, which is what we hope we'd see. There's also a little bit of cluster 4 and cluster 5 there. And cluster 5 really is something you'd expect to see in analysis of Zelda, because remember, she's giving a tilt-based explanation focusing on the angle that the rays hit at. So that should be there. And cluster 4 is a little of a surprise, but remember, there was throughout kind of a little whiff of psi-based explanation there. Okay, so that's Zelda. And the last student I told you about is Caden. And remember, Caden gave a tilt-based explanation, but in his explanation, he's focused on the fact that a hemisphere is closer rather than farther. And the analysis of Caden does look a bit different than Zelda. You see a little bit of cluster 1 near the beginning, which is the tilted conception, which we'd hope to see. There's a lot of this cluster 3, is that what it is? Cluster 3, which is the yellow bar, and that's the one that has to do with the hemispheres of the Earth. There was a lot of talk about hemispheres, as there often is with tilt-based explanations. And then at the end, in the latter part of the interview, you start to see the black bars, and that's the closer farther bit, which was a component of his explanation. His explanation was kind of built out of hemispheres tilting plus being closer or farther to the sun. Okay. So now I'm ready to sum up. So I attempted to apply computation analysis to a type of data that has a long history in the learning sciences, videos of interviews intended to study kids' prior conceptions in science. And I set out to produce analysis that's in the style of a knowledge and pieces analysis. And that meant I was trying to produce an analysis of a certain sort. I see students as possessing a number of relevant conceptions, and I want to understand how they, in the moment, they construct explanations out of those conceptions. And I said there's some notable difficulties to doing this. The amount of data is really small. The speech is halting and ambiguous, and we don't have gestures and diagrams. And even with those difficulties, I said I was going to go as far as I could with really simple methods. And my deviationalizing was the one exception there. And my results, I'm willing to confidently declare that the results are suggestive. And what it suggests to me is that it might well be possible to use computational methods to capture features of student learning that are widely recognized to be important. Okay, so what does this by me in particular? One question that I want to ask is what role these computational techniques can play in the toolkit of researchers who are interested in the study of prior conceptions. An obvious question to ask in that regard is, can we replace human coders? And whether or not that ultimately might be possible, I think it's worth emphasizing that a human, myself, played an important role in a lot of these analyses. I had to decide how many clusters to use, and even more than that, I had to interpret those lists of words to see them as meaningful. But actually, I think that replacing human coders is not where I think the big win will be for me, or researchers like me, at least not early on. Instead, I think that the biggest contribution can come from support these techniques can provide for traditional kinds of analysis. It provides a kind of independent test of validity. Okay, finally, I'm just going to quickly mention some open issues and next steps. So I did this just for the seasons. There might be something special about the seasons, so we should try other subject matter. My presentation here was pretty selective and anecdotal. Ultimately, we want to come up with some way to make a comparison to human analysts in a more systematic way. Third, it'd be nice to apply this type of method to actually answer new research questions. I didn't do that here. Instead, this was more like a test of concept to see if I could produce something like the analyses I produced by hand in an automated way. Fourth, there's a lot to be done to systematically investigate all the alternative parameters and methods there are out there. I do a little bit of that in the paper, but not too much. In the paper, I show what happens if we use different segment sizes. That's a small variation. I also show what the analysis looks like if you don't deviationalize. But there's a wide range of things we could do. And the final question, what I think is almost the most interesting question, is why this works to produce anything reasonable at all. I mean, when I analyze this data, I would never think of doing it without looking at kids' gestures or what they draw. But somehow this produces, at least in this limited way, nicely suggestive results. And I think it'd be pretty interesting for my field to try to understand why that is. That's it. Thanks.
The geek in me needs to know some things on this one. I don't understand all the vectoring and stuff that you did. But what I mean, I see what you did, but I don't know exactly why you did each of those steps. Are you drawing on some well-known means of analysis that I don't know about that was why you turned it into vectors and you did 25 words? And what conceptually was the role of each of those steps?
Well, this is within a family of widely used methods. I mean, I started with latent semantic analysis, which is almost, there's kind of a latent semantic analysis fad in education research, and I latched onto that fad. The process I went through was essentially simplifying and simplifying until I ended up with this vector space method, which is essentially LSA without most of the work. So there is a lot of standard stuff, and you can read about doing vector space analyses and clustering them in a textbook. But conceptually, the idea is that these vector space methods map the meaning of text onto vectors, and then two chunks of text have the same meaning to the extent their vectors point in the same direction. So that's conceptually what you're doing, and then you just think of these vectors as a meaning of a block of text.
One thing that would be really nice to do would be to take student exams where they have short answer questions, which were often kind of similar to this form that you've been dealing with, and be able to cluster them and say, okay, there's 6 different kinds of answers people gave to these questions. And then the instructor could say, okay, yeah, well, that one's right and these ones are wrong, and then you can teach to those particular bugs that you found. I'm wondering about your method by which you chose 7 clusters. And so this, I don't know much about this agglomeration approach to building up clusters, but it seems to me that would be really nice to automate the total number of clusters. And then we could assign a label to that cluster, which we could then use for interesting analytics. How many people have this kind of misconception? How many people have this kind of misconception? And even try and find, do some LSA with content to try and repair some of that. Could you just comment on the magic number?
So, trying to find a way to automate that is one of the things that's been most frustrating for me. I don't think, as far as I can tell, there isn't a simple way to automate the choice of the number of clusters. There's ways to come up with measures of how good a fit your model is in contrast to how complex it is. Whenever I apply those metrics, they always prefer by a wide margin the model in which there's all the clusters, all the segments are in a single cluster, because it's the least complicated model. You can introduce a parameter to kind of tune how much it weights model complexity over how well it explains the data. But then, to me, then you're just introducing another number rather than the magic number of 7. But that might be okay if across lots of domains that single tuned parameter had the same value. But in the case that you're talking about where you have lots of answers, of test answers, there's even some lower hanging fruit. I mean, if you have human coded data, then you can use supervised methods rather than unsupervised methods. In fact, so the thing that's happened to me now is my colleagues come to me and they say, I've got 1,000 students who filled out this test with short answers, and I've coded 100 of them. Can you code the rest for me? And from that, there's a very straight path to that doesn't need clustering at all, and doesn't even need vector space methods.
Sure.
Short question and short answer.
Okay.
Real quick, great job in the presentation. Thinking of applying this to large online courses. So 2 things. One, instead of discussion-based, you've got students typing in responses, which is a bit different. And 2, instead of 54 students, you have multiple thousands. How would your approach differ for that kind of a use case?
I mean, you would think it would all be easier because people tend, I think, to type out more complete thoughts when they're writing text. And there'd be a lot of data, which you would also think would make it easier. I mean, I guess the problem might be if people are too parsimonious in how much they type. That would be a problem. So here you can the interviewer can draw out the student